Here we go. As I promised last Friday, we're going to do about 10 iClicker questions to start class. Some of it, or most of it, will be on the reading that I assigned. After we do the iClicker questions, then we'll do a fairly complicated circuitry type problem. It's not a full circuit, but it's a part of a circuit that we're going to work on. And we'll have some additional reading homework in chapter 20 for Wednesday. Also, this week, I'm going to try to set up a lab maybe for Friday, and that's going to require everybody to be here on Friday. So I know there was a lot of absences on last Friday, but you want to get in here for that lab. And it will be circuits and stuff like that. So I'll try to get something simple set up for you so we can start applying these electric field and electric potential concepts. All right, now turn on your, hold on. Okay, turn on your clickers, and just so you know, this first set is going to be alphanumeric data, so you're going to have to hit the send key. All right, now, here's a problem very similar to the exam. Multiple choice, but there's 8 different choices because I'm asking you about a direction. When you guys are done, I also want to count the number of students in class. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Look it up in the book. The answer's in the book for that. I think it's in the book for that one. Okay. 84 students answered. All right, this one, here's the radial line segment. Here's the electric field. It's northeast, roughly. So let's see what you guys voted for. Yeah, most of you voted for that. Very good. A few of you were off. You know, you got to be able to do this. It's just, there's no other, you know, you just got to be able to do it. All right, let's do another question. Calculate the magnitude of the electric field at point S. Now this one, hold on. This one's numeric, so. Okay, I want a multiple of 10 to the 8 newtons per coulomb to the nearest 10 times 10 to the 8 coulombs, newtons per coulomb, and 3 significant figures, or I should say to the nearest 0.001 multiple. Now this one you're going to take some time. So hit refresh. If you don't have a number 1, does it start with number 1? All right. If you don't have a number 1, just hit your refresh key and you should be good. This one's actually numeric, not alphanumeric. And on this example, if your answer is 4.289 times 10 to the 7, your answer is 0.429. You have to type a 0 before the decimal point. You can't lead off with a decimal point. It won't let you. Okay, there's a student up here. Where is everybody? Absences over there. One there. These guys are absent. There's 2 absent back there. Type in your answer and hit the send key. Don't forget. Chris, nice to see you. Let's get to work. Kristen, what were you saying? Hmm? Yeah, and square the hypotenuse, actually. Right. Yeah, the hypotenuse, the length of the hypotenuse is the square of, but the, is this, excuse me, the length of the hypotenuse is the square root of a squared plus b squared. But for this the denominators are squares, so you don't have to square root anything. You just square the sides and add them up. What do you got?
88, she got 86.
Yeah, because Chris Montez just came in,
Yeah.
so that makes it 86.
I got 86 before he came in.
Oh,
I
all
think we're
right.
87, or I don't know. We're one off from each other, I think.
All right, that's sufficient. Yeah, see what I'm trying to, Andrew,
Oh, yeah, I'm right here.
uh, what I'm trying to do is detect whether students are using another student's clicker. So if we have if a load of 87 students here and I get 90 answers, then I ask you guys to go take a look. All right, now just circulate.
Okay.
Make sure you round off carefully. I see some people that are rounded off a little bit too far from the right answer. 2 minutes. Can I ask you a question? When you're in web courses, can you see the class photos? Have you ever tried it?
Where
Try,
are they?
try, they're in, I'm going to sign in right now. Let's see if I can. Is there a mouse here? Smart product update? No. Go ahead and log into your computer if you have a chance. Yeah, okay. What? I don't want this. Come on, baby. Dude.
They just use photos with their headshot.
Yeah, okay. I want you to set that up on this computer every day.
Okay.
All right. And I'm trying to sign into mine. I just signed in, but I'm not used to this keyboard. All right, here we go. Yeah, so I'll use it, so I'll be using this one today, but um, I wonder if the students can't do this, but I can. And
What's the difference from the two?
what's that?
What's the difference from those?
Nothing. Everybody's in both sections. It's to allow this extra long period. You know, we're supposed to have a break halfway through,
Oh, I see.
and I never do. But they have to. When they register, they have to have both. Well, this is only 9 across. So I'm just trying to make sure I have a chance to learn some of these names. See, I know some of these. Here's Christine. There's Rain. Emma. Here's Melanie Del Toro from the demonstrations. Brandon Dishman. Where's he at? He's in the back. Rachel Dupuy is over here. Marlena is over there. Vivica's over there. Alexandra, Abigail Eflin, Jason Flowers, Carly, Isabel's over there. Isabel, you guys almost done over there? Hurry up. 30 seconds. To breathe. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 87 submissions here. Okay, let's take a look at your. The correct answer is 0.721. Um, so there's your correct answer. Now, I want to look at some of these. Now this one rounded off too much, 0.72. If I was asking for the nearest hundredth of a 10 to the 8 Newton per Coulomb, then you'd be kosher. But um, I don't know what the 3.712 is. Here's another three. Now here's another one down here. Another round off or scientific notation problem, I guess. Um, and here's one. This is a round off problem here. That's somebody that should have rounded off to 0.722, but that would be wrong. Yeah, I don't know what these 3.7s are. 18 million, I don't know what that is. Anyways, 0.721 is correct. So let me. All right, next question. Yeah, but that's right. It's KE over R squared. R squared is 20 times 10 to the minus 18 meters squared. You know, the numerator is 1.418 times 10 to the minus 9 Newton meters squared per Coulomb. So it's the exact same calculation from the exam, except that it's a proton down there instead of an electron. And all that does is reverse the direction of the electric field vector, but not the magnitude. Question. CJ, did you have a question? Okay. Flowers. Yeah, so just so you know, I use 9 times 10 to the 9 simply because that's what I remember. So make a note of it. And yeah, you can, if you go to the National Institute of Standards and Technology, NIST.gov, you can use, it's 8.98762 times, something like that, times 10 to the 9. But we'll just go with 9. All right, and consider it to be 9.00000, okay? And we'll let the other number and 1.602 for the charges, and then whatever the distances are. All right, Emily, sufficient? All right, Emily, Emily, And everyone, this is my expectation. That's why we're practicing it. All right? Now that you know the correct answer, I want you to be, you can use, work it out when you're studying tonight. Double check, make sure you can get the right answer. Question. What is your name again? Mackenzie. Okay. The question was, when do you do Pythagorean theorem first instead of figuring out the x and y components? The answer is you always do it first because in order to do the x and y components, unless you're on the x-axis or something, or in the y-axis, directly above the proton or directly to left or right, you're going to have components of some kind. You can't do that until you get the magnitude of, the vector. All right. So you get the magnitude of the vector, which means do your Pythagorean theorem, a squared plus b squared. A squared here is 4 nanometers quantity squared, and b squared is 2 nanometers quantity squared. Total of 20 square nanometers, which is 20 times 10 to the minus 18 meters squared. All right. So you got to do that first before you try components. All right. And then, you can do a 2x4 triangle here. And that's, can you switch me over to document cam? Oh, hold on. I don't want to show everything. All right. Here's come on, doc cam. Let's turn it on. Can you figure out how to turn this on? Is it on? Is that the on button up there? Oh, there we go. Okay. Switch out, switch back. All right, switch back. All right, here we go. All right, so here's my calculation, and look at my trig. I'm just using a 2x4 triangle, Mackenzie. To do the trig. You see, I got my square root over there, 4 over square root of 20. That's the same as 2 over square root of 5, which is what we had on the test. This is slightly different dimensions, but it's the same basic. It's a similar triangle, so 26.6 is. You see my r squared. So at the top of my paper, 20. See that? There's my Pythagorean. So that's what I do first. Then I set up my trig because I know I'm going to do it. But you guys didn't know that. Where is she? Mackenzie, what's your last name? You had to think for a second there. B-O-N. M-O-N? Oh, M-O-N. We got all your guys' mug shots up here. I gotta learn your names. Down here, okay. All right, very good. All right, so anyways, Emily, there's my calculation. All right, you can see it. And we talked about it. Or, you can see that's kind of cut off there, but. All right, switch back to laptop, please. All right, next question. Also, alphanumeric, or excuse me, also numeric. Oh, all right, go ahead and calculate. Ah! Okay, Emily, you got the answer here. See if you can verify the answer. Doggone. You know what the problem is when my cursor's not clicking over the screen here. The cursor's over here. It doesn't. This the PowerPoint doesn't obey. This defeats the entire purpose of the exercise. Well, nothing to do it now. I see everybody's typing in their answer. Nice. sure that this, see this time delay, dragging it? That's the other problem. Eduardo, Eduardo, how you doing back there? Yeah, aren't you Eduardo? Yeah, how are you doing? Did you verify it? You're not going to do it. All right, 10 seconds to get your vote in. 5, 4, 3, 2, 1, 0. Yeah, so go ahead, switch over to document camera. Here's the rest. For those of you that are still struggling a little bit, we're going to keep working on this kind of a task. Here's the x component. 2 over square root 5 times whatever the magnitude is. And that works out to 6.448 times 10 to the 7, or 0.645 times 10 to the 8 newtons per coulomb. All right. Now, it's my expectation that you can hack this at high reliability. This and other more difficult problems. So we're just going to keep studying this, and we're just going to, keep working on it. I mean, there's nothing else to do. Okay, slot me over to the laptop, please. All right. Now we're going to do a few iClicker questions from the weekend, from the reading, which I saw at least one person reading right before class. That's all right. Yeah. Yeah. This the student's question was, how do you get that 2 over square root of 5 business? You got to know your trig. You got to know how to handle vectors, which you should. I mean, I'm expecting that everyone has learned that technology in Physics 2053. The cosine comes in from, go to the document cam. Get this out of the way. What's the definition for cosine? Adjacent over hypotenuse, right? So in this case, and I'll show this on the screen here in just a second. All right, so here's your basic concept. There's your vector triangle. The electric field vector itself is the hypotenuse, and EY and EX are the components. Angle theta down there, and you can. And what is your name again? Holly. Holly, you can use angle theta down there, or if you like, you can use angle alpha up in the upper corner. But you're always going to come down to, if you're down to this. See this equation? So you solve for EX, E sub X. You cross multiply E to the left side, and you have E times cosine of theta. And for this triangle, the cosine is 2 over square root 5. All right, so that's how you do it. All right, and it's this basic. Does that look familiar? Like from previous? Yeah. So, all right. Can you switch me back to laptop? Okay. Prepare for multiple choice. Yes. Peanut. Well, I could have used 4 over square root 20, but I secretly know that reduces to 2 over square root 5, so I just made it. But I could have written it 4 over square root 20, and it comes out to the same number. All right, so we're going to do some multiple choice. Have your clicker ready. And this one's going to be true multiple choice. You just click. All right, you don't have to hit the send key. Capacitor is a device that, if you did your reading over the weekend, you know the answer to this, especially if you looked at my annotations. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 88 answers. Let's see what you guys voted for. Yeah, good job. Most of you voted for that. Okay, now that's a cinchy one. And you know what my standard procedure is to work with some basic ones, get you all thinking, and then work my way up in difficulty. So we're just at the bottom of the mountain now. We're just now a mountain, for those of you here in Florida that are born and raised here, a mountain is this thing. It's shaped kind of like this, and it's basically a big rock. It goes way up into the sky, and you can see way far away, 50 miles away when you get to the top. And if you ever, I used to live out west in Montana, so lots of lovely hiking. Anyways, you go to what they call the trailhead, which is where the trail starts to go. You a little parking lot, and and you park your vehicle and you hike up the mountain. So we're just getting out of the parking lot with this question, but we're on our way up the mountain. Question 2. So this is kind of now on a test, this would be a 2-point question. Or in homework, this would be a 2-point question. 20 seconds. Kendra Kordak. Right there. The mugshots. UCFPD mugshots. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, plate size, applied voltage. So, Volt for volt, if you have a bigger plate, you have a little bit more capacity for pushing electrons in there. Now, did anybody vote for C? I mean, well, C is tempting because plate separation is also a physical factor. The closer the plates, the more charge you can drop in there. But the kind of metal used, not so much. Just has to be a conductor. Okay. So copper versus aluminum versus gold, you're not talking a huge thing, except for price. All right, next one. Now we're getting down to the nitty gritty. And when I'm giving you comments after each question, you should consider those to be notes or things to take down in your notes. Benjamin Mans. Oh, there you are over there. Okay. Sitting right next to Peter and Andrew. Andrew, right? Andrew Cheshire. Peter Johnston. And who's that guy on the other side of you? Salim. Okay. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. What happens to the stored charge? Well, let's take a look at your guys' answer. If you guys were to tell the tale, there'd be a lot of different stories here. All right. That's what this tells me. So let's talk it over. Okay. So, oh, I forgot to stop it. This day, two screens. I have a hard time adjusting the screen size here. Okay, this is better. All right, um, so what's the story? The stored charge is reverse plates. No, not really. That would happen if you had a total breakdown of the air between the two plates, right? In other words, a spark. If there was some kind of an insulating material like paper or plastic or something, which in a regular capacitor there usually is, then it would burn a hole through the insulating material. Stored charges. So there's the breakdown there, right? You disconnect the battery. Stored charges do stay put until the circuit is reconnected. So you reconnect that circuit. So make a note of that. You load up that capacitor and then disconnect it from the battery. You got some stored charge in there. Now, are they permanently stored there? No, they are not. All right. Option D, the stored charges disappear in a fixed amount of time. The capacitative time constant. Well, it turns out there is a time constant, but not in this simple of a circuit. Right? We're going to be getting to that this week. It's called the RC time constant. All right, what happens to the electric field? Again, we have the break in the circuit. Read carefully and make an answer. I see people discussing it. That's really good. Thinking it over yourself and talking it over with your study group is good. – 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 87 answers. Very good. The answer is C. A bunch of you voted for option B. And you know, B is half correct. The charges do stay put. That's what we had in the last question. But the electric field isn't going to disappear. You got unbalanced charges left and right. So what is it? Chopped liver? It just goes down the drain? No way. Right? Now D is also appealing because it sounds, like ultra geometric concepts. Electric fields turn 90 degrees and become parallel to the charged plates. But let me look at this. I don't think I tempted anybody successfully. No, I did. I got one person to bite on that one. And I'm not being facetious really, because about getting a student to bite. If you think about it, I mean, you guys don't write multiple choice questions for a living, but I do. It's part of my job. And the theory is first of all, you have a question, and one of the options, A, B, C, or D, has got to be correct. And then you want another option, at least one, that's tempting to some degree. All right. And then maybe one or two that are not as tempting. Now, the tempting one here is B. Right? That's what we call a distractor. Now, if I can shake you off of C and onto B, that means you haven't got it yet. You're not solid. But if I can give you B and C and maybe D, and if I can't shake you, I got you right where I want you, and all the answers will be locked onto C. You'll be confident. Now I'll do that in lecture as well. If you volunteer an answer, you know how I get people to stand up, which is nice in this classroom, getting people to stand up and recite, just like in grade school. You recite an answer, I might try to shake you, just to see if I can shake you. Like if somebody said, I might say, well, D is pretty tempting. I mean, after all, the electric field lines would be parallel to the plates. And I could maybe, if you were not solid, I'd maybe be able to shake you on that, right? If I try to trick you that way, that's my devious way of getting you to shaking you. But if I can't shake you, you're good. All right, let's keep going. Now, here's where the tire hits the road. When one reconnects the capacitor to a tiny hair dryer, what happens to the hair dryer? Read carefully and think. Talk it over with your 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. We got some splaining to do. So let's take a look at this. And notice I shut off the question before I showed you the answers. All right, so this is basically what happens. Most of you, let's see, what's the percentage on that? Actually, 53% voted for that. Um, there's no battery. We're assuming that a hair dryer is basically a bunch of wires that, maybe run a little motor, um, a little electric motor that blows air, and another goes through some heating coils. Do you ever look inside? Or like a toaster. Toaster has little heating coils in there that get hot and blows air if it's a hair dryer. But no, there's no storage. So you're not going into a battery again. All right. All right. So nothing happens is that would be correct if we reconnect it to the same battery because it's already loaded. If we give it enough time, it'll load up to max, and then the battery can't do any more unless you put a bigger battery, and then you can reload a little bit more. So nothing happens. That would be good for putting a battery in. Electric field is static, so no current can flow through the hairdryer. That's kind of a non sequitur because it's talking about the field inside the capacitor and current flowing through the hairdryer. Oh, did I say the word current? Yes. Go ahead and write that down as a vocabulary word. Current, voltage, current, capacitance, and more. We're going to have more vocabulary words in there. Stored charges move nowhere. The stored charge moves nowhere because the hairdryer is not a battery. That is incorrect. And that's exactly what happens. It's not a battery, so charge does move. And so you get a little bit of hairdryer action. All right, next. True or false? 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Oh my goodness. There's a little bit of disagreement here. Only 81% said true. 19% said false. Yeah. Here's another way to think about this. Instead of putting a hair dryer there, what if you just took the two wires and brought them close to each other? What would happen? Just like a millimeter apart. What would happen? What would you see? Now, you wouldn't see an electricity. What would you see? A spark. Yeah. So a spark produces light. You'd see the light from the spark. All right. So the charges are going to move if you connect it in a circuit. And they cause that electric motor to do a little work. And the heat did a little bit of thermal work, heating up that stuff, a little delta Q. Yeah, so that's good. Now let's do some alphanumeric, and let's do this one. So hit the refresh key, type in a letter, and this one I'm going to grade every answer correct. because this is more like a public opinion survey. But give me your best thought. Now my best thought, by day or by night. 20 seconds. Joel, what was that? I saw you're moving your arm around like. It's round? Equipotential lines, yeah. Lines of equipotential, yeah. Yeah. No, you don't have that here. You know what, the lines of equipotential are parallel to the surfaces. Yeah, parallel to the plates, right? Because they're always perpendicular to the field. So if the field's going straight to the left, to the right, then you're, yeah. So in other words, at a right angle, perpendicular. Or as they say in the math department, orthogonal. Orthogonal, yeah. Yeah, it's a bunch of. All right. 5 seconds. 5, 4, 3, 2, 1, 0. Let's see what the combination. All right. So we got a spread of answers here. A little bit of a bunch of B's and C's, and some D's, and one E for none of the above. Now I'm going to grade all these correct. Not right now, but after class. Let's look at the correct answers. It does store energy. And this is a concept that I actually alluded to in the textbook. Yeah, the concept that the electrical field itself carries energy. And this is an electrostatic field. So it's not electrodynamic. You know what's an electrodynamic electric field? Light. Light transports energy and momentum from point A to point B in space-time. Now, this is not electrodynamic, it's electrostatic, but you would still say that the field stores energy. Another good answer, B. There's electrostatic potential energy in the electric field. And guess what? Guess how it shows up? It's proportion. Go ahead and write this down in your notes. The electrostatic potential energy is proportional to the square of the field. The electrostatic potential energy is proportional to E squared. Now that's, for us, that is enormously important. And in fact, I've already alluded to the fact of how it's important. The electromagnetic field, light. E squared being the energy is related to the energy of electromagnetic fields is immensely important. I can't overemphasize it. And that's what we have here. Now I want to continue and give you a little extra instruction before we dismiss on capacitors that are hooked together in one circuit. Now there's two basic ways to do it. Hook them up back to back, or as we say in physics, in series. And when you have that, let me get rid of this banner down here. This is a diagram from the textbook. So the series of three, capacitor 1, 2, and 3 are up above, and they're actually equivalent to a single capacitance. Now, here's the kicker. The thing that has to be true for this circuit, you're hooked up to a battery in this case. So you have a certain amount of voltage between the plus and the minus. All right, it could be 12 volts or 1.5 volts or whatever the voltage is for the battery. Now, over on the capacitors, The top plate of capacitor 1, let's say that that's at high voltage, 12 volts. The next plate down, the negative plate of capacitor 1, is not going to be at 0 volts. It's going to be somewhere between 0 and 12. The one that is at 0 volts is the bottom plate of capacitor 3. That's where all the delta V is. All right, between the top plate and the very bottom plate for capacitor 3. Now, in between, we got that other plate we haven't even talked about, or that other capacitor. Now, when you and if you look in the annotations, I wrote out a long formula for delta V. All right, and the other thing that is true for both plates of each capacitor is the charge load, plus and minus Q, top and bottom in this diagram. Now, the reason that that's important is because the voltage is equal to Q over C. All right. Now, if you look at the bottom diagram, the one capacitor that replaces the other three mentally replaces it. The equivalent capacitance, plus or minus Q, high and low, and the delta V of the battery, whatever it is, 12 volts, for instance. All right. Now that's Q over C EQ, the equivalent capacitance. Now in the book they put down C subscript S, but I don't like that notation, so I'm going to use C EQ. All right. It's a little more generally used. Now, the delta V, now here's what happens at the capacitors. There's a little bit of delta V at capacitor 1, a little bit more at capacitor 2, and the last of the 12 volts gets dropped at capacitor 3. You're writing this down? You're listening? It's going to be on YouTube. Now, see, so you might have like 2 volts dropped at capacitor 1, 9 volts at capacitor 2, and then 1 measly volt at capacitor 3. You know, there's going to be, and it depends on the capacitance. Now, the Qs are the same for each. So for each capacitance, for each capacitor, it's Q over C. So the voltage drop for number 1 is Q over C1. The voltage drop for number 2, Q over C2. The voltage drop for number 3, Q over C3. And on out, if you have, 1,000 capacitors, you just keep going. All right. So there's general formulas up there. Now they all have a numerator of Q. Just look at the diagrams. Top plate, always a Q. Bottom plate, always a minus Q. Whether it's the initial configuration in figure A or the equivalent configuration in figure B. All right. So those Qs, guess what happens to them? Benjamin. What happens to them? They cancel. Yeah, that's right. They cancel. And so you're left with 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3 plus blah, blah, blah to 1 over C to the whatever, your last one. 100, 1,000, whatever it happens to be, however many you got. Now this diagram, it would be 1 over C1 plus 1 over C2 plus 1 over C3. So if you're trying to figure out what the equivalent capacitance is on the left, you got to do a bunch of fractions. And everybody loves those a lot. I know that from my experience. I don't see everybody smiling. I hardly see, Maria, you're hardly smiling. Now she's smiling. Salim, do you love fractions? Good. That's the correct answer. You have to keep telling yourself, I love fractions. I love fractions. Anyways, you're going to have to deal with fractions on the right side. And then to get your, Melanie, to get the equivalent capacitance, you do all your, common denominators and stuff, get all that into one fraction on the right, and then you flip-flop it. And that'll be your equivalent, So you got to remember at the end, do a flip-flop. All right, and that'll be CEQ. All right, now you're going to do a problem with this in just a few minutes. Okay, Jordan, so It's coming. You're going to have to use this. You're going to have, I think it's two, what is it? Two series and one parallel to that. Now, parallel, here's what parallel means. It means you have separate parallel routes to the battery. So the first capacitor, so there's three in parallel. So a charge can go out of the, we'll think of it as a positive charge on the move, out of the positive terminal of the battery up to the top of capacitor 1. And then charges are going to leave the bottom of capacitor 1 and head over to the negative battery. But that positive charge, it could just as easily go over to number 2, the top of capacitor 2. And because that capacitor has its own separate route to the battery. Okay, Krishna? Yeah, so you separate route. So in other words, you could take, a pliers or some wire clippers and totally cut out C1 and C3, and you still get a load on C2. No problema. All right, that's what parallel means. Now, and then you got C3 over there. It's got its own parallel independent path to the source of charge, to the battery. All right, so they're all going to load up at the same time. Now, the top of Q1 and Q2 and Q3, they're all connected to the top of the battery. So that's your 12 volts up there. Those are the 12 volt plates. The bottom of Q1, the bottom plate of C1, C2, and C3, those are all 0 volts for a 12 volt battery. All right? So the voltage equation, again, boils down to, it ran off the page. Sorry. That's basically battery voltage on the left equals voltage from the first capacitor, voltage from and so all those things add up. All right. Oh, excuse me. That's the charge load in terms of the voltages. And the voltages are all the same. So basically, all you have to do is add up C1 plus C2 plus however many you have. The way that I like to think about it is parallel capacitors are equivalent to one big plate or one big set of plate, one pair of really big plates. And that's what diagram B shows you. All right. So get that into your notes. Parallel capacitors, one pair of ginormous plates, depending on how many capacitors you have that are parallel. Now, if you have a little bit of each, you just gotta, work it out. All right. Now, I'm gonna give you 15 minutes to work on this problem. And this will be let me change to numeric. Actually, I'm not going to do that. I'm just going to give you this problem because I think the answer is in the book. Is the answer in the book? Gosh, I shouldn't have blabbed. All right, try to work this one out. You should get it. Do your equivalent resistance on the left, and then you have two parallels, the equivalent of the first two, and then capacitor number 3 over there. See if you can verify the book. All right, so go ahead and circulate. Okay, stay there, and you're going to have the microphone. Okay, students, let's review. And for your listening pleasure, Daniel here is going to. Can you switch over to Doc Cam? Daniel is going to explain how he did it. Okay, and so let's go ahead and here's the calculator over here. So he'll show you. Let's back this up a little bit. All right.
So I like redrawing the diagram just so I don't have to be looking at the screen constantly. And then because these two are in series, you're going to do 1 over 10, which is that. Sorry if you can't read it, my handwriting is kind of bad. And then 1 over this, and then you add those together, and that gives you about 2.433. So I'll do that on the calculator.
Show the calculator over a little bit. All right, so there it is, and this is we've got it in floating notation right now, not scientific notation. So 3.433 repeating.
And
Anybody remember getting that? Yeah. Okay.
And then you need to invert it because these are in series. So then you just do 1 divided by 3.433. And that gives you 0.291.
Okay.
And then you say 2.5 because it's not in series, it's parallel. And you just add these two together and get your answer.
Yeah. So the equivalent resistance in the first calculation, the 30 and the 0.3 and the 10, are now part of one big plate with the 2.5 microfarads. Right. So that's the explanation. And Daniel, I have one more thing to say to you.
Yep.
Thank you very much. Everybody give him a hand. And this is a little bit better than going up to the board, I think. Anyways, thank you, Daniel. All right, now, can you switch me back over to laptop? That was very good. Okay. Your homework assignment for tonight and due on Wednesday, read up to chapter 20.2, and I'll start class with another 10 questions in iClicker. All right? You're dismissed.